This
permanent
conference
engineers.
will now be recorded.
Right, I'll start again. Good afternoon, everyone. My name is Michael Woolford. I'm one of the permanent way engineers working for ACOM on the South Rail Systems Alliance and was the track design engineer for 9 Elms Junction. So 9 Elms Junction is a renewal of 9 S&C units in southwest London, located between Vauxhall Station and Queenstown Road Station. The renewal was delivered over Christmas 2020 on an 11-day blockade. And just to give you a bit of context of the layout, we've got 3 crossovers, 1778, 1780 and 1781 Alpha Bravo, located at the London end, which are all sat on top of each other and have been sort of phrased as a triple crossover. And then moving towards the country end of the layout, we've got 1784 points and 1786 Alpha Bravo, which form the junction for the diverging lines of the up and down Waterloo curves, which carry around to Linford Street Junction on the AHG lines. So in terms of the existing layout, we've got £113 rail on timber bearers throughout. All 9 S&C units are FES 24 switches and crossings and hardwood through bearers. And the triple crossover, we have 4 through alignments there with all tracks tied together on a single through bearer of approximately 13 to 14 metres in length. We've got numerous HP switches in the existing layout, and in terms of the engineering drivers for the renewal, there was a history of broken crossings in the layout, along with poor horizontal and vertical alignment, and the layout getting increasingly difficult to maintain due to the decay of the through bearers. And we are situated on a viaduct as well. And then in terms of the proposal, Grip 3, there was a look to rationalise the layout and remove initially 1781 Alpha Bravo, which was one of the crossovers in the triple crossover, and also to remove the crossover 1786 Alpha Bravo from the junction. This wasn't carried forward through to the approved single option, and the design that was handed over to the South Rail Systems Alliance at Grip 4 was for a full renewal, like for like modern equivalent form of all 9 S&C units. So we've got 756 FES 24 switches and crossings on concrete. And there was also a look to standardise the track intervals through the crossovers to 1970 throughout on all 4 lines. As part of the Wessex route requirements, we needed to include underbearer pads as well throughout. And also we undertook some rail wear analysis using TrackX to determine if we needed to include any new HP rails within the layout, and also look at the overall site lubrication. But as the project developed, it was identified at Grip 3 that there would be no suitable build-up area for S&C panels, and there was no option of getting panels delivered to site via road. So the design that was handed over to us was for a triple split modular layout, which meant that we effectively had 3 bearer joints in the triple crossover. And due to the reduction in the track intervals down to 1970 throughout, we ended up with an overall length of the bearers at 12.84 metres. We held some very early discussions with STE and the technical authority within Network Rail, and ultimately it was the technical authority that gave us permission to proceed with the installation of the triple split bearers. And just prior to the first national lockdown back in March 2020, in the month before February, we held face-to-face meetings, which were quite invaluable to get representatives from South Rail Systems Alliance with Design and Construction, STE, the Route Asset Management team for track, manufacturers, and the project management team. We also had a very detailed involvement from the route asset management with the development of the triple split layout, particularly in terms of where the joints were positioned. And there was a further request over and above the triple split layout positioning to actually remove quite a significant number of bearer joints, and this was achieved using slave bearers. And also there was a focus on the learning outcomes from the Court Hill derailment a few years ago, and how we would manage the risk and what mitigations we put in place for such a complex modular layout. As I said, we carried out some TrackX analysis to determine our HP rail requirements, and again, detailed RAM involvement in the development of this. The results from that were put forward to the RAM, and our recommendations to include new HP switches, and those positions were agreed with the RAM. As part of the mitigation for managing differential settlement in the layout, we actually moved away from the original trackbed investigation recommendations, which was proposing to include a 1 in 30 crossfall in the layout, but to maintain a consistent ballast depth throughout the layout, and particularly under the modular joints. It was agreed that we would move to a level formation throughout. And due to the fact that the triple split arrangement had never been done before, there was also a requirement to produce new REPW drawings, and these were produced using the manufacturer's 1:50 drawings. And then ultimately we had permission granted from the head of track within Network Rail to the asset manager to sign off the Form A design and ultimately approve the use of the triple split bearers. And there was also obviously consultation with the structures team within Network Rail on the Wessex route to move to the concrete bearer layout, a significant weight increase on the viaduct, and also to use the Kirov crane as part of the construction methodology. And the delivery of the S&C and all the manufacturing drawings were produced by Progress Rail. So moving on to some of the design challenges along the way, particularly with the split bearer layout. Just to start with, just have a look at the track diagram in a little bit more detail. So what we've actually got at 9 Elms is a number of the crossovers in the triple split section. The crossover routes actually form the main trafficked route within the layout and see the most tonnage. And therefore, looking at the below REPW drawing for a FVS 24 modular layout, we actually started to look at how we could move a lot of these joints away from the areas which were taking the most loading in the layout. So this is actually what we came up with as an initial proposal as a triple split layout. We've got effectively the 3 crossovers fully modularized as triple split. We did have to do a little bit of fettling initially just to reduce the number of joints in the layout, because due to the staggered arrangement of the crossovers, we actually ended up with a significant number of additional joints required around the end of the through bearers and where the closure panels are on the switches. So we actually utilised a lot of short-ended bearers in these locations to make sure that we weren't increasing the number of modular joints over and above the standard layout. And then moving on from that, with all the discussions we had with the asset management team and with construction to make sure that the panels could be broken down into something that could be physically constructed on site and delivered to site, we then looked to actually rationalise the standard modular layout. So there was quite a significant focus on protecting the crossings. Of course, they're subject to most of the loading within the layout and high dynamic forces, so there was a focus to move those sections and the supporting gauge rail to a continuously supported bearer, but also moving some of the joints away from the crossover routes and into the through routes, taking into account the varying traffic levels and the tonnages within the layout. And ultimately, this is what we ended up with. So as you can see, we've got a significant number of the crossings have either got no joints or have had the joints moved away from them. And actually what we ended up with from Progress Rail in the manufacturing drawings was 2 manufacturing drawings for each layout that we had at 9 Elms. We took a similar approach on the junction at the country end as well in terms of how we position the joints. But because we were using slave bearers and the panels needed to be delivered on tilting wagons, we actually ended up with the previous arrangement here as a delivery layout. And this is our final installed layout. And due to the nature of using all the slave bearers, they were delivered loose to site. It meant that we had quite a lot of loose leg sleepers as part of the relay. So we actually provided setting out coordinates for all of the through bearers on the layout. And just to give you an idea of the number of joints involved, we've got 113 bearer joints in the overall triple crossover, reduced down to 9 triple split bearers, 26 double split and 34 single split bearers. And equally at the junction of 1784 and 1786 Alpha Bravo, no triple split bearers in this layout, but we did have 23 singles and 22 doubles. As mentioned earlier, set out coordinates provided for all of the through bearers. So just give you an overview of the actual sort of stripped back AFC drawing. We'll start at the London end, and what we've got, just initially something to point out, we've got 2 pairs of insulated joints just in front of 1780 Alpha and 1778 Alpha. These were the signalling overlap joints for the signal gantry at approximately 1 mile 70 chain. And due to the reduced overlap, these joints could not move any closer towards London on the right hand side, which pretty well fixed our S&C positioning for those 2 crossovers. Slightly more staggered arrangement for 1781 Alpha. And as we move through the layout, you can see the final modular arrangement in the crossovers. And then moving through to 1786 and 1784 points, we've actually got the junction itself is actually on 20mm cant as well. So we've got a short sort of 20-meter transition in here as well. And then moving through the junction, you can see we've taken a similar approach on the modular arrangement, where we've removed or simply relocated the joints away from the crossings, prioritizing those that are used the most in terms of the through routes and the crossovers. And then towards the end of the renewal, 1786 Bravo points on the up and down Waterloo curves. So in total, we had approximately 700 yards, 740 yards of plain line renewal on top of all of our S&C. In total, I think it was circa 1,000 meters of renewal across all lines. And what I'll do now is I'll just hand over to Constantin, who will take you through some of the coplanarity challenges of the junction, which, as I said, sits on 20 millimeters cant. So I will stop sharing now and hand over to Constantin.
Good afternoon, everyone. I'm Constantin Ciobanu. I'm the track design CRE. I was the track design CRE for this job. One of the challenges that we had with this project was the coplanarity design of it and the vertical alignment arrangement through the junction. So the challenges related to this are also due to the fact that the design layout that we had for the junction, which shows here in various colors the alignments that we had for the layout, was not matching what actually was happening from the point of view of the train running layout. So upwinds line is running through the crossover into the upwinds line on the other side, and downwinds is doing the same. So our main alignment from the point of view of the train running is through the junctions, which obviously we had to consider when we developed the design. The other issue was in the area of the double junction at Ayman Legend, where the arrangement here, which is canted with 20 mil cant, had to be designed as coplanar to avoid any vertical misalignments for the split bearer layout. The main challenges with this were due to the fact that the distance measured along the main route of a turnout is not matching the distance measured on the turnout route for each of the bearers. And as we go through the turnout away from the switch, that increment in variation differs. So this is becoming a challenge from the point of view of the design development. And the other thing very important here that was that due to the complexity of the layout and to allow an accurate installation, we had to provide all the alignment combinations as .xml files to be used for installation and to allow flexible damping. So for this, we had to provide an accurate coplanar vertical alignment for all the lines, and obviously to check and validate these results in a most accurate manner. So what we did initially was to develop a first draft vertical alignment, matching the gradient on all lines and start and end elevations. We're expecting to have, considering this, some errors, but minor. But when we cross-check this, we noticed that the elevation errors around the crossing noses were about 5 to 13 mil level difference. So we had to consider this very carefully in designing this. I have to say that it is, in a way, odd to have this difference considering how low the cant is, 20 mil, but the complexity of the vertical alignment, the change, creep, and all the other factors brought their influence into this. So what we did first is to look at the design formula that we have in 2049 and to consider it carefully. So the formula from the point of view of the geometrical definition is right. However, the labels that we have are misleading in a way. G here is not a gauge, but the rail center line to center line distance, and also the track interval is not the 6 root, the running edge to running edge measurement, but also a track center line measurement from the canted rail to the low rail of the adjacent line on which you want to calculate the coplanarity. R, it's in this case the cant. So one of the issues is that these distances that are shown in the current version of the standard are not running edge to running edge distances as it is shown in the figure, and the labels are, as I said, misleading. And if we would have considered them as running edge to running edge distances, at the crossing, around the crossing nose, considering that the width of the rail is about 70 mil, we will already have an error of about 1 mil in elevation difference. And for the width of the junction rail-to-rail measurement of 5.9 meters, that error would have become 5 mil. So this 5 mil is part of the errors that we saw initially. So obviously we had to consider the formula in the right way. And as I said, the formula is right geometrically. The labels are not to be considered. One thing that we need to consider also is that for our design process, we measure the distances in a horizontal plane. So this distance S plus G is matching the track centerline interval between the tracks on which we do the calculation. However, D is a horizontally measured distance, and I can't base the distance between the rail center lines is an inclined dimension. So that for higher value of cant, that thing is also to be taken into consideration when this issue of coplanarity is delicate. In our case, the error would have been in considering the formula as is defined in the standard, the error would be well below 1 mil for the dimensions that we had in the layout. So this was one of the things that had an influence on the initial error that we saw. The other thing was that, as I said, at every bearer, the distance between that is distance measured to the switch, the point where the two tracks are together and they have a matching elevation. The distance difference is different on the main line relative to the one measured along the turnout route. Obviously, for a canted alignment, this needs to be considered because that adds an incremental difference in the vertical alignment. The result being, in fact, instead of a matching coplanar gradient of the main, the result would be a kind of a complex parabola, considering how the gradient in difference of distance varies along the two routes. In this case, the issue was even more complex because, as I said, the up Windsor line labeled here, which in fact is not up Windsor line anymore because it has moved on this route and it's up Windsor on this side. It is up Windsor from the point of view of the label that we used as design. So just to be clear with the labels here. This line here is the main route on the 7086 alpha, but becomes the terminal route of 7086 Bravo. So we had to take that into consideration when we defined our vertical alignment. And the result was, considering the cant that we have and the accurate formula for coplanarity, we define 3 gradient segments for up water rule line and 4 gradient segments for down water rule line. This matching that curve that is a function of the distance to the switch relative to the main and turnout line. And by doing this, we removed 4 mil of error on the up water line and the maximum figure of 8 mil on the down water line. And we achieved a fully coplanar layout for that 20 mil cant, which, as I said initially, we thought that would not be that significant. So the result of this combination of correct coplanarity formula and split vertical alignment design produced a fully coplanar layout for all our 4 tracks. Obviously, we had to check we are right with this approach. One way we did that was to create cross sections in ventral rail track using sleeper cells that were designed to match the gauge and cant of the layout that we had. And we measured in CAD the coplanarity error of this new design. And the errors were, as shown here, relative to the reference plane of rail of the down Windsor fast, up Windsor line. The maximum errors were 1 mil on down Waterloo line and 1 mil on up Waterloo line. On this one, we couldn't, the error was 0. And from the point of view of the figure that we see here, I think a significant influence has also the rounding. So the figure was below 1 mil rounded to 1. We had another way of checking this. We defined in Baker rail track the coplanar surface relative to the reference track, which was down Windsor fast, up Windsor. So we defined based on the rail centerline string, rail centerline strings for this track, we defined a coplanar surface, drawing it across the junction, and then we measured relative to this surface what's the difference in level between the rails designed in drawn in CAD of all the other lines, all drawn as the standard indicates correctly, as rail center lines, not as gauge distance at 1502 mil. And the level difference between these strings and the surface was again ±1. So practically we achieved to a measurable accuracy the compliant coplanar design for all the tracks of the layout. And this allows us to produce all the design combinations required for tamping this section and ensure from design perspective the entire that the entire alignment set is coplanar. So returning to our previous section, we had to run the combination of the track running from one alignment to the other and to define the vertical alignment on each of these segments as accurate as we could. Another thing that we've done was to run track X analysis, as Michael mentioned earlier, to check if it is possible to remove the requirement for HPE rail on the switches and for this junction. However, considering that the main running route on the lines is through the crossover of the junction, and the fact that the layout is practically matching the existing, except the minor optimization from the point of view of the 6-foot distance and of the arrangement of the layout, that was not possible. So in the end, the TrackX analysis suggested that the HP rails are still required, and was decided that all the points shown here would be required to have HP rail switch sets. That would be all for my presentation. I'm passing now the screen to Sean. Thank you. You can start, Sean. I think you are muted.
There you go. Right, that's the one thing I forgot. Thank you, Constantin. So thank you, Constantin and Mike. So I'm Sean Murray. I am Technical Director at ACON. But on 9 Elms, I was the Contractors Engineering Manager, the CEM for the works. I'll begin, basically, I'm going to talk through some of the multidisciplinary integration. I wouldn't say the challenges, there are some successes that we've did, and also on some of the planning, design and construction planning that we had to undertake as well for Christmas and going forward from there as well. So just a reminder basically about the South Rail Systems Alliance. I've said this before in the previous presentation for PWI, is you know, our approach to the work we do is not about S&C renewals. We treat the system, it's a railway system that we are designing, it's not just a track renewal. So the term like for like in modern equivalent, that is used, we still use that. However, the Alliance continued to deliver this to see if we could get some efficiency and sustainability. And that's what our stakeholders and the industry are looking for, especially at the moment in these post-COVID times. So as it always is with our S&C designs, it is the track team, the permanent way team. They're the dominant discipline leading the design development, and we have our partnering disciplines include the signalling, civils, electrification, power, collaborating to produce this integrated design. So I'm going to talk a bit more about those disciplines and some of the work they had to do or lead even rather than the track team. So just a bit of a description of some of the work that was undertaken. So as Mike said earlier, the layout is pretty constrained. It is a small corridor with the viaduct, with adjacent Windsor lines as well, with the Waterloo and Windsor lines that we weren't touching. So it's pretty constrained, and we had to do quite a bit of other discipline work in that. So signalling was the usual, replace the point motors. Conversion of a number of the track units to EBI EBI 400 tune track circuits, which I'll come on to a bit more in a second. And the existing signalling power arrangement meant we were changing some batteries and battery chargers located in an REB, but that then brought with it some new equipment that we had to put into the renewal. So if just keep that in mind first of all. The points heating, again, MEF, modern equivalent form renewal, and there was some existing equipment which presented some safety and access issues, and again I'll come on to that. Third rail, conductor rail, nothing really special again in that. There was some improved gapping that we had to do for future and current stop types, so there was a bit of extra design we had to do there. And again, moving conductor rail around to from the 7 to the 6 foot to get some safe by design items in there as well into the design, again because of the tight space and access issues. And civils played a big part in the design as well, multidisciplinary design. So they were brought on board to support relocation and renewal of line side equipment and the cable routes. And I'll show you some of the existing situations and then what we did to integrate our designs. Hopefully, there you go. So, so signalling, just a couple of pictures there from the existing layout. So on the right there, you can see how constrained the access is. So it is red zone band. However, it's still difficult to actually get into any of the cable tropping because you've got the ET cable sitting on top of the tropping, and some of the load cases, the signalling location cases, are also sitting very close and tight to the parapet, on the parapet, and tight to the walkway safety barriers there. So on top of that, for the renewal, we had to renew these and also have the EBI 400 track circuit in, which was presenting us with even more additional infrastructure, railway furniture and cabling. So we needed space for that. We needed something to do something with the cables while we were there because the trough route was very full. and we'll be adding more cables into the corridor due to the upgrade of the power supply and what we were changing for the power supply and the batteries. Points heating, again, in terms of the renewal, there's nothing particularly special about it apart from what was existing. So again, on the right there, the picture on the right, that's the position of where the existing PHTs were, the points heating transformers were. They were sitting in a very unsafe location on top of the parapet wall, against the hand railing, okay, and to actually get to the PHTs, you have to lean through, and you can only basically get to one side of the PHTs. So not a good position, and we raised this as a safety by design issue, an opportunity, and decision was made to actually remove these from the parapet and that position and move them to a safer location. And we did this in consultation with a route asset engineer. Who obviously, if we're there and the opportunity's there, let's do that. Okay, so we did move these in the end to a safer position, which was part of an integrated design. Some more pictures there. So this is more at the country end, and again, you can see the tight space at this end to supply points heating equipment, and you've got the associated equipment due to ECE cables, signaling cables, LOCs, the point zone telephone, the viaduct retaining wall. It's very congested there, and on top of that, there was some maintenance sort of debris, I would say, left there as well, some materials, and it's all in a very tight space, and see the vegetation as well. So again, we had to do some work around that area to try and get the equipment into a safer, more accessible position. So in terms of the design, as I said earlier, our approach to the design, that's not you know, innovative or not groundbreaking to those that work on this type of project day in, day out. But we on 9 Elms projects, we use 3D modeling to a much greater extent than we would do for a number of our renewals. So we used it for the majority of the disciplines. And what I'm showing on the screen here is the example of where we put the points heating transformers. So these were moved along with the PHCC off the parapet wall and at ground level close to the access point. It was about 170 meters countryside of the existing positions on the viaduct. Points heating took the lead on this rather than track, obviously. So they took the lead, they positioned the equipment, and civils and signaling had their input into the sizing and the location of the trough routes, the foundation-based designs, and consulted with track and ETE on the cable routing issues. There was especially some of the clash detection of the cables and clearances to ground level equipment in the railway corridor. So, you know, it's not innovative as such. It's just that for 9 Elms we paid a lot more attention to this to ensure that we did good clash detection, good cable separation. We knew where all the routes were going to go and that we had the space for it in this constrained location. There we go. Okay. And this is the same area and an extract from the civils design, which provided the specific details of the points heating civils work that needed to be done to help it. So the points heating design, 3D design, that was used as a reference design for civils to then do their detailing and put more focus on the troughing, the how we're attaching any troughing to the top of the parapet, which was the original suggestion to try and move that out of the cess area, hand railing, and how we attach to the viaduct wall going up as well. Okay, so a bit of a different approach for this one in terms of other disciplines trying to lead the design and having an integrated 3D design. ETE, so the top extract we have there is from the proposed cable management extract from the ETE design. The bottom one is the proposed negative bonding. It's easy to see that both designs identify cables where they're required to cross the track layout, and also where the impedance bonds are located with the IRJ positions and AWS magnets. So you can see that there's a lot of equipment in a pretty constrained area, and we have to comply with separation rules for signalling, with ETE, and also with proposed locations of welds and the S&C. And I think I've got to say a bit of a saviour here was the reduction in welds, for one, because we would have really struggled otherwise to position a number of equipment. So what I'm demonstrating here is the S&C configuration. It imposed an additional constraint in relation to cable routing and cable management. The signalling, as I said to you earlier, this EVI track circuits, it's an upgrade. These things are an upgrade to the long-established TI-21s and the EBI track 300 track circuits. So they would normally be used as jointless track circuits, and they can be terminated with IRJs, which is the approach at 9 Elms. And there are rules on where the EBI units are placed. For example, distances from the IRJs and the cable length to support that information back to the units, and also clashes with other signalling equipment and ETE 4-foot equipment. So these, we had to understand exactly where these could place in the railway corridor, but also in the 4-foot, in terms of how constrained the layout is, the 3 crossover layout. So I think Mike alluded to this earlier. In total, we had 95 cable management sleepers, straight bearers, okay, in the whole for the double junction and the triple split crossovers. We had 95. We had to manage those along with point C and ETE signalling through the layout, and obviously making sure that we get the EBI units in and EWS units in, etc. to cross and get the equipment and to reach the equipment over on the CES side. We now routinely, as ACOM and the World Alliance, now routinely provide a cable management plan, which is used by all disciplines to coordinate our cable management requirements. So we will have on there cable management sleepers, the signalling and ETE bonding, signalling tails, cable trough routes, UTX requirements, etc. This will be used to make sure we coordinate all of our sort of cross-track and line-side cable management. The site teams, they still require their own discipline-specific designs, and the cable management plan provides a confidence of the integration, the space, and the manufacturing requirements. So we do also share this with the manufacturer, so they've got a bit of an idea where we have CMSs, cable management sleepers, within the layout. They know where they're going to be, and hopefully they'll place those in the right place when they turn up on site if they're on the panel. And so a lot of work goes into these, and it's now the norm with the South Rail Systems Alliance projects. We always do a cable management plan, which will give confidence to each discipline that we've integrated all the cables and all the route requirements as well. So all of that's fantastic, got to say. So we had a fantastic integrated design in place. We had a really good integrated construction plan around it for the core works being undertaken during weeks 38 and 39. As Mike said earlier, Christmas 2020 to New Year 11-day blockade. However, circumstances on the circumstances on the first day of work changed this on Christmas Day. I'm not going to go into the incident in detail. We're still looking. Well, I say there's still investigations that I think they've concluded, but it's not public knowledge yet. So I'm not going to dwell on the incident itself, but I will discuss the good work and collaboration of many parties to make sure we got the railway up and running after the blockade, and how we completed the outstanding work within a very short period after Christmas, well, after the New Year. So some brief points on this. So the failure happened about midday on the afternoon of the 25th of December, Christmas Day. First day of the blockade, and it was very, whilst this project was happening, all the way through this project, we knew this was a one in a lifetime chance to get in there and do a big amount of work. So we could not just say, right, we've had an incident, we need to stop. We had to make sure we could do what we could do because of access. The Waterloo curves, they were planned to be re-energized later on anyway. So we had stored a lot of the, well, all of the track materials on the Waterloo curves. So they weren't due to be commissioned at the end of the core renewal anyway. But even with that, we did have some dislodged equipment, signalling equipment, and some of this equipment was for the route, okay, so for the whole of the railway, not just 9 Elms corridor. So we needed to make sure we got some signalling and power and telecoms equipment back on. And for this, we had to revisit our designs, revisit integration, and revisit the testing and commissioning plans. And that's testing and commissioning, not just for signalling, but for all of the works, track, EMP, power, etc. So with that, we had also a good plan of how we were going to install it. So this is just the first part of the plan. And this construction plan was based on plain lining with the Windsor reversible first, which was the most northern track against the viaduct parapet. Following this, we're scrap out the middle, up Windsor and down Windsor fast, then the down Windsor slope. So the plan enabled us to have a nice wide formation and bottom ballast billiard table, basically. And as Mike said earlier, these were lessons learned from the Court Hill derailments and the modular installations around the country. So the plan was there to try and make sure we had a lovely, we needed to do it line by line, scrap out, and then have a nice flat billiard table for the whole of the area. The incident kind of derailed this a bit. So the plan was quickly changed. So we weren't able to install the Windsor reversible, the first track that we wanted to put in. However, with route discussion and the route team, especially the civils team on the route, were able to prepare the formation and bottom ballast at least. So we gave that a single whack. We had space to install long bearer sections to be relayed in the Windsor reversible, which I'll show in a second. I said there about the S&C panels, which still had Waterloo curves. We were very conscious that the parapet wall had to be reconstructed in good time for the Windsor reversible to be installed at some point. It wouldn't happen on the core, but it would have to happen at some point in the near future. And we had to understand any monitoring on the behaviour of the structure and the track, and that was prior and during and post works of the structure in particular, just to make sure we weren't putting any additional pressure on the structure, and we worked very closely with the route for that. In green here, that's the extent of the area where we had to reconstruct the wall. And due to the modular location, due to the location of the modular splits and the long bearers, we were able to separate out 1781 alphas, which is shown there in grey. So again, the splits allowed us to separate it out, so that point end wouldn't be going in. But we were able to install the up Waterloo lines, the B end of 1781, which is just off the page. But note in the previous photo I showed, we also needed to prepare the unused track bed. Okay, so the track bed that's sitting in here, we still had to prepare it to make sure we could put the routes, the long bearers, the long bearers in at least. And we worked with the road asset team to agree how we would safely install and tamp that section, which was adjacent to the required rebuild of the wall. Just photo there of the billiard table approach. That's on the double junction. You can see the amount of area there that we have dug out and scrapped, and those in, ballast in, and be compacted. Previously mentioned, we were able to install the majority of the long bearers, as you can see there. So majority are in. You can see the shrouds are off on the ends of some of these, hopefully. Okay, so we're able to install the majority of these along with a nice formation. Mike said earlier, the track designers provided additional information to the track construction team to set out the track. So along with the old-fashioned string and pegged core, we provided coordinates for all the long bearers, and I was on site that day seeing them actually properly use the coordinates and being able to very quickly place the long bearers in the right position. We there's some more bear photos of the installation of the long modular bearers on Zen Boxing Day. Okay, so that's the B end being put in, and the A end, which is the end we wouldn't be putting in, and the wind's reversible to the left there. There we go. So yeah, perversely, it was fortunate that the space left by not installing the remaining point end. It meant we can have somewhere to place equipment. So there we were able to use that space to put some location of some temporary location cases for signalling, and also to be able to bring back up any cables to support the railway. So yeah, perversely, it was great that we had a nice flat area, but we knew we had to then pick that stuff up and move it into its permanent position at some point. Okay, so the main things we did was the load cases sitting in the kind of unused forefoots there as well. Obviously, the wall needed to be built back up and any damage to the structure rectified before we were able to complete the installation. And we worked with the Wessex Route Structures Asset Management team to determine a design for the rebuild of the parapet wall. It was especially important to design the railway furniture integral. So these are the old cases, and we worked with the team, with the asset team, to make sure that we had a integral design for the new cases. And we had to also work with them to tell them to define any boundaries between us. So we had construction boundaries and design boundaries. And the constraints defined the type, so the boundaries and constraints define the type of construction plant we were going to use, taking into account loading and vibration, the position of the plant in the area, and that's based on the this zone of influence, basically. Okay, so we use this zone of influence to define where we could work, and how close a triple whacker could work to the wall if the plant's still capable of achieving the spoiler removal quantities and the compaction values required. So we had to make very good, big decisions on what plant we were going to use, how we were going to operate them, and where we were going to operate them jointly with the route asset teams. Okay, just showing some of the envelopes. So we had an excavation envelope and the ballast and compaction envelope defined that the construction team worked to. Just a couple of photos there of us installing the remaining point end, so you can see the viaduct wall, parapet wall there, fully rebuilt. The bridge drainage was installed as well by them, together with a containment membrane surrounding the pipe fill material, and they did some deck repairs to the deck waterproof membrane. Space was obviously then left for us to come in to install the cable routes, cable trough routes, access level, taking it off the viaduct wall now, the new viaduct wall, and the lopes were installed by the Alliance. So the team, and they're sitting there, so they did all of the parapet wall, they did the base for us, and we put in the lopes, and we managed to actually remove one of the design lopes due to efficiencies in design between the two periods. So there was a lot of work done in a very short time scale. I would say over, we've got 7 weeks, I would say. We managed from Christmas to mid-Feb to finish off the works. We had a number of telephone conferences, especially immediately during the blockade week. We then had very weekly big progress meetings with stakeholders, with route assets, and between us we had a number of IDCs, and these all produced really good integration and coordination conversations between us, route, and all of the designers. We've improved our IDC IDR process for structural assurance, and I think that's now gone nationwide, hopefully, in asking the right questions of the asset engineer team. And the designers are also assisting on site with engineer verification. One example is some live gauging assessments that we do now with the construction team. So so AECOM, as a designer, we're going out and helping the contractors with their verification. So just to finish this off, 9 Elms in total. A really good example of collaborative working, I feel. One of the more enjoyable projects, renewal projects I've been on, although they're all enjoyable. But Network Rail Technical Authority and Wessex Group Asset Management, absolutely brilliant in communicating and talking us through our proposals, as Michael said earlier. Progressive Design Assurance was spectacular with Network Rail, and we got a Cat 1 Form B track design acceptance. For such a complicated layout, it was great to see that we got a Cat 1. As I said, communication was really good between week 39 and 47 to get a good integrated design with Safe by Design solution during that time. And it was all delivered in very highly challenging global times. We weren't able to see each other face to face as much as we could do. Working from home, we saw each other on site, obviously, but it was very, very challenging times, not just for the Alliance, for everybody. And I'm pleased that we worked through that to deliver a really good solution in the end. Okay, so thank you very much.